2.2 Limit of a function and limit laws. The outline of this video is as follows. We will discuss the core concept of a limit, starting with an informal definition to build our intuition for how a function behaves as its input gets arbitrarily close to a specific value. We will also learn the standard notation used to write these ideas down precisely. Next, we will examine the key ways a limit can fail to exist, such as when a function jumps, grows without bound, or oscillates too much, which helps clarify the boundaries of the concept. With this foundation, I will introduce the fundamental limit laws. These are the essential rules that allow us to systematically calculate limits for combinations of functions, like sums and products. Finally, we will apply these laws to solve a common problem known as an indeterminate form, like 0 over 0, where direct calculation fails. I will show you how to use algebraic techniques like factoring to find the true underlying limit. Now I will introduce the informal definition of a limit, which is the central concept for understanding how a function behaves near a particular point. We say that the limit of a function f of x as x approaches a number c is another number L if we can make the function's value f of x as close to L as we want, simply by choosing an x that is close enough to circa. It is crucial that this works as x approaches c from both sides, the left and the right. We write this relationship as the limit of f of x as x approaches c equals L. For example, a function might approach a value of 2 as its input gets closer to 1, even if the function has a hole or is undefined at exactly 1. The key idea to remember is that a limit describes the intended destination of the function, not its actual value at that point. Let us explore a powerful idea by looking at a function's behavior near a point where it is undefined. I have a function here, f of x equals the quantity x squared minus 1, all divided by the quantity x minus 1. If we try to plug in the value x equals 1, we get 0 in the denominator, which is not allowed. However, for any other value of x, we can algebraically simplify the function. The numerator factors into the quantity x minus 1 times the quantity x plus 1, which allows us to cancel the x minus 1 terms, leaving us with just x plus 1. Now it is clear that as x gets closer and closer to 1, our simplified function gets closer and closer to 1 plus 1, which is 2. This value the function approaches is what we call the limit. So the limit of our original function as x approaches 1 is 2, even though the function itself does not exist at that specific point. Here we will explore a critical distinction. The limit of a function as x approaches a point does not depend on the function's actual value at that point. This leads to two important consequences. First, a limit can exist even if the function is undefined at the point we are approaching. Second, the limit can also exist even if its value is not equal to the function's value there. For a concrete example, notice how all three functions shown in the figure have a limit of 2 as x approaches 1. This is true even though the first function is undefined at x equals 1, and the second function has a value other than 2. Only for the third function, h of x, does the limit as x approaches 1 actually equal the function's value, h of 1. The essential idea to remember is that a limit describes the trend of a function near a point, not its specific value at that point. Now I will establish two fundamental limits that act as the building blocks for calculating more complex ones. The first is the limit of the identity function, where f of x equals x. This case is very intuitive. As the input x gets closer to some number c, the output, which is just x itself, must also get closer to circa. For example, as x approaches the number 2, the function f of x equals x also approaches 2. The second key limit is for a constant function, where f of x equals k, for some fixed number k. Since the function's output is always k regardless of the input, its limit as x approaches any number c will also simply be k. If f of x always equals 7, its limit is always 7. Remember that these two simple results are the starting points we need to evaluate the limits of more complex polynomial and rational functions. A function does not always have a limit at a given point, and it is important to recognize the three common ways a limit can fail to exist. The first case is a jump, which occurs when the function approaches two different values from the left and the right. For example, a step function might approach 0 from the left side of an input, but jump up to approach 1 from the right side. Second, the limit fails if the function grows too large, meaning its value increases or decreases without any bound as it nears the point. A classic example is the function 1 over x, which shoots towards infinity as x gets close to 0. Finally, a limit does not exist if the function oscillates too much, bouncing endlessly between two fixed numbers. A function sine of the quantity 1 over x does this near 0, never settling on a single value. In all these cases, the function fails to approach a single, specific, finite number, which is the core requirement for a limit to exist. I want to introduce a set of powerful tools called the limit laws, which help us find limits of complex functions by breaking them into simpler parts. The core idea is that if we already know the limit of a function f of x is L, and the limit of another function g of x is m, we can combine their limits arithmetically. For instance, the sum rule states that the limit of the quantity f of x plus g of x is simply L plus m. This same intuitive logic also applies to finding the limits of their difference, product, or a constant multiple. The one rule to watch carefully is the quotient rule, which says the limit of f of x divided by g of x is L divided by m, but this only works if m, the limit of the denominator, is not equal to 0. Essentially, these laws let us evaluate limits of combined functions using the same arithmetic we use for numbers. To complete our set of limit laws, I will introduce the root rule, which allows us to handle functions under a radical sign. This rule states that the limit of the nth root of a function is simply the nth root of that function's limit, L. In other words, you can pass the limit operation inside the root. There is one important condition. If n is an even integer, such as for a square root or a fourth root, the limit L must be positive, since we cannot take the even root of a negative number in the real number system. For example, the limit of the square root of x as x approaches 9 is the square root of the limit of x, which is the square root of 9, or 3. The essential takeaway is that you can find the limit of the function first, and then take its root, as long as the result is a real number. Our fundamental limit laws give us a powerful shortcut for finding limits of polynomials and rational functions. For any polynomial function, the limit as x approaches a number c is simply the value of the polynomial at c, which means we can find the limit by direct substitution. This idea extends to rational functions, which are fractions of two polynomials, with one crucial condition: the denominator must not be 0 at the point circa. For example, to find the limit as x approaches -1 of the fraction x cubed plus 4 x squared minus 3 all over x squared plus 5, we just substitute -1 for x everywhere. This gives us the quantity negative 1 plus 4 minus 3 in the numerator, and 1 plus 5 in the denominator, which simplifies to 0 over 6, or just 0. The key takeaway is that for these common functions, finding a limit is often as simple as plugging the number into the function. Now let us explore a key technique for when direct substitution gives us the indeterminate form 0 over 0. This result is actually a clue that the numerator and denominator share a common factor, which we can eliminate to find the limit. Our strategy is to first factor both the top and bottom of the fraction. For example, consider the limit as x approaches 1 of the fraction x squared plus x minus 2, all over x squared minus x. Factoring gives us the quantity x minus 1 times the quantity x plus 2 over x times the quantity x minus 1. Since we are interested in the limit as x approaches 1, and not the value at 1, we can safely cancel the common factor of x minus 1. This leaves us with the much simpler limit of the fraction x plus 2 over x. Now direct substitution works perfectly, giving us 1 plus 2 over 1, which equals 3. Remember, when you see 0 over 0, look for a common factor to cancel. I will now show you a powerful algebraic technique for finding limits involving square roots, which resolves the kind of ambiguity we just saw with calculator estimates. This method uses what we call the conjugate, which you can find by simply flipping the sign between two terms. For our problem, the conjugate of the numerator is the square root of the quantity x squared plus 100 plus 10. Multiplying both the numerator and the denominator by this conjugate is the key step. This removes the square root from the numerator, revealing a common factor of x squared that we can cancel. After canceling, we can directly substitute x equals 0 into the much simpler expression. This gives us 1 divided by the quantity square root of 100 plus 10, which equals 1 over 20, or 0.05. So, using the conjugate is a reliable way to find the true limit when numerical methods might fail. I will now introduce a powerful tool for finding tricky limits, known as the sandwich theorem, which allows us to find a function's limit by comparing it to two others. The idea is straightforward and follows two conditions. First, we need a function, f of x, whose values are always trapped, or sandwiched, between two other functions, g of x and h of x, near some point c. This means g of x is less than or equal to f of x, which in turn is less than or equal to h of x. The second condition is that both of these outer functions, g and h, must approach the exact same limit, which we can call L, as x approaches circa. Think of g and h as two converging paths. If f is stuck between them, it has no choice but to follow. Therefore, the conclusion of the theorem is that the limit of our middle function, f of x, must also be L. This is how we can find the limit of a complicated function by squeezing it between two simpler ones. Now we can see just how powerful the sandwich theorem is for finding the limits of functions that are difficult to evaluate directly. Let us start with an unknown function, u of x, that is bounded between two other functions. We are given that u of x is greater than or equal to 1 minus x squared over 4, and less than or equal to 1 plus x squared over 2. As x approaches 0, the limit of the lower bound is 1, and the limit of the upper bound is also 1. Because u of x is squeezed between them, the sandwich theorem tells us its limit must also be 1. We can use this same logic to establish two foundational trigonometric limits. Since the sine of theta is always between negative absolute value of theta and positive absolute value of theta, and both of those bounds approach 0, the limit of sine of theta as theta approaches 0 must be 0. Similarly, we know that the quantity 1 minus cosine of theta is squeezed between 0 and the absolute value of theta. This forces its limit to be 0, which in turn means the limit of cosine of theta as theta approaches 0 must be 1. Now let us look at a straightforward but important rule for how limits interact with inequalities. This theorem states that if one function, f of x, is always less than or equal to another function, g of x, near a point c, then their limits must follow the same relationship. In other words, the limit of f of x as x approaches c will be less than or equal to the limit of g of x. However, it is critical to understand that a strict inequality between the functions does not guarantee a strict inequality between their limits. For example, for any non-zero value of theta, the function negative absolute value of theta is strictly less than sine of theta. But as theta approaches 0, their limits are exactly the same, they both equal 0. So, remember that an inequality is preserved when you take the limit, but a strict inequality can become an equality. Let us briefly recap the key ideas we have covered about limits. We started with the fundamental concept that a limit describes the value a function approaches near a certain point, which is an idea that is independent of the function's actual value right at that point. To calculate limits systematically, we established a set of limit laws for common combinations of functions like sums and products. For more challenging cases, especially the indeterminate form of 0 over 0, we saw how algebraic techniques like factoring or multiplying by a conjugate can reveal the underlying limit. Finally, we introduced the sandwich theorem, a powerful method for determining the limit of a function by showing it is trapped between two other functions that converge to the same value. Together, these concepts and tools provide a robust framework for analyzing function behavior. To finish up, I want you to try 2 review problems that bring together the key techniques we have discussed for evaluating limits. The first question asks for the limit as t approaches -1 of the quantity t squared plus 3t plus 2, all divided by the quantity t squared minus t minus 2. Remember, if direct substitution gives you the indeterminate form 0 over 0, that is a strong hint to simplify the expression algebraically first. The second question involves a function, f of x, that is bounded by the inequality 2 times cosine of x is less than or equal to f of x, which is less than or equal to 2 plus x squared. This structure is a classic setup for using the sandwich theorem to find the limit as x approaches 0. Please pause here and work through these, as they are excellent practice for identifying which method to apply.